Hello and welcome back to Joe Bailey Revision. Today we're looking at Physics Topic 7, which is all about atomic structure. So let's start with the structure of an atom. So atoms are very small. They have a radius of 1 times 10 to the power of minus 10 meters. They contain a positively charged nucleus, which is made up of neutrons with no charge and protons with a positive charge. Also in atoms there are negatively charged electrons, which orbit around the outside of the nucleus. These, of course, have a negative charge, but the negative charge of the electrons is the same amount as the positive charge of the protons, meaning in a regular atom there's no overall charge. Electrons are arranged in shells, and the electrons that are closer to the nucleus have a higher energy level. So this energy level can increase if electromagnetic radiation is absorbed because it gives it energy. However, it will decrease and the electrons will move further away from the nucleus if it loses electromagnetic radiation. So next let's look at an example. So this is Na sodium. So its mass number is 23 because that's the proton number plus the neutrons. And its atomic number is 11, which is just the protons. It makes sense if we think that the mass is concentrated at the nucleus, the majority of the mass is all in there, that only the protons and neutrons factor into the mass. So if we look at this, we know from here that the protons is 11 and that the mass is 23, which means the neutrons must be 23 minus 11, so the neutrons must be 12. Isotopes have a different number of neutrons, meaning they will have a different mass number, but will have the same atomic number. And positive ions have less electrons, because for something to be positive, if you take away negative, it becomes positive. In a similar way to if you minus a minus number in maths. 2 minuses make a plus in that way. So obviously negative ions have more electrons. It goes the other way around. So next let's look at development of the atomic model. So the first model we have to look at is the plum pudding model, which was made by J.J. Thomson in 1904. It was created after the discovery of electrons. It made sense back then. Basically, the idea was that an atom is a ball of positive charge with negative electrons embedded within it. So the entire thing would be positive, but there'd be electrons just scattered around inside of it. So next we found out the nuclear model, and that this proved that there was the existence of a nucleus, and that the nucleus was positive, and that electrons orbited around this nucleus. So we found out this because Rutherford did this experiment and he found that some alpha particles, when he fired them at an atom, were reflected, but only a small amount of them. So he decided because of that, mass must be concentrated in the middle of an atom, which means there must be something there, which he found out to be the nucleus. So next, let's look at Bohr. So Bohr found out that electrons orbit the nucleus at specific distances. So he found out all about shells and how that works. So next there's Chadwick, who figured out that neutrons are in the nucleus. So he figured out that there was a third particle in the nucleus with no charge. Because before they thought, oh, the nucleus is just protons. But he proved the existence of neutrons. So now let's look at radioactive decay. So some atomic nuclei are unstable and they give out radiation to become more stable, and that's the process of radioactive decay. So because they want to become stable, they give out the radiation. So there's 3 different types, but first let's look at alpha particles. So alpha particles have a high ionizing power, which means they're very dangerous and can do a lot of damage to things like the human body. However, they also have a low penetrating power, which means they can be stopped by paper or 5 centimeters of air. So that's why it's not particularly harmful to us, because it can't get into the body. So next let's look at this example. So there we got radon turning into polonium plus helium. So as we can see, the radon loses 2 protons and 2 neutrons. And as we can see, the helium gains the 2 protons in the atomic number underneath, and also gains 2 neutrons in the mass number above, because as we know, the mass number is the protons plus the neutrons. So we can see the mass is lost by 4 and the charge is lost by 2. And this is all because it's forming this new alpha particle, which is the same makeup as helium. So next let's look at beta particles. So beta particles have a medium ionizing power, meaning they're less harmful and do less damage than alpha particles, and they also have medium penetrating power, and they can be stopped by thin aluminium or a few meters of air. So beta particles are basically fast-moving electrons. As you can see from this reaction here, an electron is created, and this carbon turns into nitrogen, and this happens because one is added to the charge. Because if you think about it, if you're taking an electron away, which has a charge of -1, you're adding extra charge because you're taking away a minus again, as we said earlier. So yeah, this electron is taken away as a separate thing and becomes the beta particle. So next, let's look at gamma rays. So gamma rays have a low ionizing power, which means they're not particularly dangerous to people. However, they have a strong penetrating power. They're unstoppable in air, and they can be stopped by thick lead. However, the strong penetrating power isn't that much of an issue because of the low ionizing power, so it won't do much damage. Gamma rays are basically energy, and all the atom loses is energy, so we don't need to worry about any equations for that. So next, let's look at half-lives. So half-lives, a half-life is the amount of time taken for half of the atoms in the radioactive material to decay. So after every half-life, the amount decaying halves. So it slowly decreases by half. So let's look at an example here. So an example, a half-life equals 30 minutes. So if the half-life is 30 minutes, in 30 minutes the radiation would be the original radiation divided by 2. And in 40 minutes, after the second half-life, the radiation would be the original divided by 4. And in 90 minutes, after 3 half-lives, the radiation would be the original radiation divided by 8. So we can see it divides by 2 every time, and this would keep incrementing, meaning that the 4th half-life would be a radiation of the original divided by 16, and it would just keep going in the same process. Of course, something divided by 4 is the same as dividing it by 2 twice, and dividing by 8 is the same as dividing by 2 3 times. So next, let's look here. Radioactive decay is random. You might need to remember that. That basically means it can occur randomly at any time. Count rate is the number of decays per second, and you might need to use that in a question. Different radioactive isotopes have different half-lives. So things that have longer half-lives, that increases the time they can be used for. So that's useful for products such as smoke detectors. Shorter half-life things, the time of them ends quickly. So that's useful for things like medicine, as they are not going to be harmful to the body because they will be disposed of quickly and just like slowly melt away. So now we've learned all about nuclear radiation, let's look at its uses. So the 3 different types, of course, because they're different, have different uses. So alpha particles are used in smoke alarms, and this is because smoke blocks alpha particles, and when the alpha particles go across, that creates a current, meaning that the alarm doesn't sound because it knows the current is passing through. However, when the smoke blocks it, the current decreases because the alpha particles can't get past, and this triggers an alarm to sound, showing that this process has occurred, meaning that the smoke alarm sets off. So next we've got beta particles, and they're used to test the thickness of paper. So this is by measuring how many beta particles are let through something. So yeah, then let's look at gamma rays. Oh yeah, and the counter in the thing, the Geiger counter, that tells us how many beta particles, is often linked to the roller, so it can change the actual pressure of the roller, meaning it changes the thickness in real time. So next, let's look at gamma rays. So gamma rays are used to image internal organs. And this is because they have a high penetration power, meaning they can enter the body, but also low ionizing power, meaning they're not damaging. And yeah, it can be used to detect if a kidney is blocked, as the radiation won't flow out of it. And that's one way to find out if a kidney is blocked or if other places in the body there is a blockage. So next, let's go over to nuclear fission. So nuclear fission is not a natural reaction, and it occurs when a stable isotope is struck by a neutron. So an isotope absorbs the neutron and brings it in. It then becomes unstable and splits apart. And because it splits apart, large amounts of energy are released. So 1 kilogram of uranium-235 creates more energy than 2 million kilograms of coal. So yeah, this neutron hitting it makes it unstable and makes it split, basically, simply. So yeah, also there are chain reactions that occur in it, but this can be controlled in a nuclear reactor by things such as boron rods. And nuclear weapons are basically uncontrolled chain reactions. The chain reaction keeps going off, which makes it more and more dangerous and makes a massive explosion. So let's look at our equation here of nuclear fission. So here we've got uranium-235, as we said earlier, and we're adding a neutron. And this splits it into these two other elements, which are made up of the two things. However, it's the things that are missing from it are 3 neutrons. And these 3 neutrons then carry on and continue to split. And because these 3 neutrons are fired into new things, that will mean it'll split again and it will create even more neutrons, and this can carry on. That's how the chain reaction takes place, as these create fission again. So next, let's look at nuclear fusion. So in the process of nuclear fusion, 2 small light nuclei, not light nuclei, they are nuclei that are light, fuse to make one heavy nucleus. And it's used to power the sun and other stars. And let's look at an example of it. So here we got 4 hydrogens fusing to make 1 helium, plus a load of energy. This is what happens in the sun. And we can see it makes sense that we have 4 hydrogens, that's turning into 4 heliums, because the thing is, it's got 1 as the mass number here, but we're timesing that by 4 to get 4 up there. So it makes logical sense. However, for fusion to occur, hot gas or plasma has to be incredibly warm. It has to be at least 150 million degrees Celsius, meaning that in the current day, it costs more energy to heat this than is received, so it's not worth doing. And there's a reason why this has to be so warm. It's because the nuclei usually repel each other as they have the same charge. However, only if we have this much energy can we create a fast enough speed that no longer matters, and we basically break the laws that would stop them from joining together. So yeah, that was atomic structure, show a bit of revision. Thank you for watching. This is of course paper 1, so thank you and goodbye.